If your real dataset is full of NaNs and quick fixes, either crash training or leak target information, you need a safer pattern. We will explore missingness in Python. Choose simple imputers and plug them into a clean pipeline. You have messy production tables and models that look fine in the notebook but fail in deployment. You want a small, repeatable recipe to impute without leaking test or production information into training. By the end, you will understand train-only imputation, how to detect leakage, and how simple missingness indicators can make models more honest and robust. I'm Professor Pi, teaching AI foundations from basics to advanced with simple, concepts-first Python that helps you solve bigger real-world problems. Handling missing data is not glamorous, but it is everywhere. Missingness breaks pipelines, biases validation, and hides real signal. The core task is simple: fill or represent empty cells so the model sees consistent inputs. The danger is leakage. If you compute imputation statistics with the whole dataset, you let future labels or test features influence training. That gives over-optimistic performance and brittle deployments. The intuitive idea is twofold. First, compute imputer statistics only on training data. That keeps the pipeline honest. Second, consider turning missing locations into features. Missingness itself often carries information. Strengths are simplicity and reproducibility. Weaknesses are that mean imputation can hide multimodal patterns and can hurt models that assume zeros are real values. We will build a tiny demo that mirrors a real workflow. We create a small feature matrix with intentional NaNs, fit a simple linear baseline using training-only imputation. Measure the leakage you would get if you used full data statistics. Add missingness indicators to see if the model benefits. And finally, simulate deployment on new rows with NaNs. Now we start with data generation. This snippet creates a tiny, realistic dataset with intentional missing values. We use NumPy's random generator to build a 12x3 feature matrix X and a binary label Y that loosely depends on the first column. Then we inject NaNs into a few cells to simulate the kind of breakage you see in messy, real data. The variable X holds features, Y holds targets, and the NumPy isNaN function lets us count how many values are missing. This setup gives us something small but non-trivial to work with in later steps. The printed count confirms the exact volume of missingness we must handle. I mentioned the random seed and fixed sizes, so results are repeatable and our later comparisons stay meaningful. Next, we will impute using training-only means and fit a baseline linear model. This snippet imputes training-only means and evaluates a tiny linear baseline. We first compute M with NumPy NaNmean on the training rows only to avoid leaking test distribution into pre-processing. Using NumPy where we fill NaNs in XTR and XTE with the same training means. Where we fill NaNs in XTR and XTE with the same training means. Where we fill NaNs in XTR and XTE with the same training means. The least squares solver finds linear weights that minimize squared error, which is a fast analytic baseline for regression or score fitting. We predict on the held out rows and threshold at 0.5 for binary labels. The variable S is the fraction of correct predictions on the test slice. If you increase the train size, the model may generalize better. If you shrink it, accuracy can wobble. The printed accuracy gives a baseline to compare against later interventions and helps us judge whether imputation choices matter in this toy task. Then we measure how much those training means would shift if we used the whole dataset. This snippet measures how much full data imputation would shift training means. We compute MAll using every row, which is the leaky approach because it lets test set information influence pre-processing. Then we compute MTR from training rows only, which is the correct approach for unbiased evaluation. Taking the average absolute difference between these vectors gives a single, easy-to-read shift value. The variable shift summarizes how far the leaky statistics drift from the proper ones. A larger shift hints at more severe leakage risk. The printed value shows how much your imputer would have been biased if you had relied on full data statistics. And that number guides whether you must fix pre-processing or not. After that, we will try making missingness explicit to the model. This snippet adds missing value indicators to make the model aware of NaN locations. We horizontally stack Boolean flags next to the imputed features, turning missingness into informative binary signals. The variable ZTR contains the augmented training features, while ZTE holds the augmented test features. We fit a new least squares model, W2, on ZTR, and compute S2 on the test slice. Then compare it with S1 from the earlier baseline without indicators. Adding indicators often helps models distinguish real zeros from imputed values. If indicators help your data, gain rises. If not, it stays near the original score. Be aware that indicators increase feature count and can interact with regularization or correlation among features. Finally, we will simulate how this pipeline behaves in production on new rows with missing values. IsSnippet simulates deployment by predicting on a small batch with NaNs. We reuse the same training-only means M to impute X new, ensuring production uses the same statistics learned from training data. The variable Z new holds the filled features, and we compute a simple probability with a sigmoid over the linear scores Z new at W. The sigmoid produces values between 0 and 1, so you can use them as probabilities or threshold them for decisions. This mirrors how a real model pipeline would transform, score, and emit probabilities for downstream systems. Adjusting the threshold would trade precision for recall, depending on your use case. The printed list shows stable, human-readable probabilities for new rows. In a real project, this toy maps directly to a deployed pre-processing step. Replace least squares with logistic regression and wrap imputation plus indicator creation in a single training pipeline. Persist the training-only means an indicator order to production, so the model always receives the same feature layout. Add basic monitoring that tracks the fraction of missing cells over time to detect distribution shifts. Recap: what it is: a train-only imputation pattern that treats missingness as an explicit part of the feature set. When to use it: whenever your data contains non-trivial NaNs and you want honest validation and stable production behavior. One caveat: mean imputation is simple, but can mask complex distributions, so validate with diagnostics and consider richer imputers if needed. Next step: swap the least squares baseline for logistic regression with L2 regularization, and cross-validate the regularization strength to see if the missingness indicators still help under a probabilistic model. If AI Foundations and Python help, subscribe and watch the AI Foundations videos.